So the only thing that's new in section 5.4 is this statement. Maybe I just repeat it over here. If ft
Just one line.
is equal to that, fn e to the j omega nt, what is the output? Using the principle of linear superposition. If the transfer function or the frequency response is h of omega, okay, if you know that you have this transfer function, h of omega, that is governing the linear time invariant system, and you have an input, you have an output, and this is the input, what should the output be? Say this is f of t, y of t. How would I write the output? The sum of n, very good, and what? Okay, sum of n equals to 1, and then real part of h of omega times the input times e to the j omega nt. Okay, this is the statement in section 5.4 that is different from what I have told you before. But I still have a mistake here that I deliberately inserted. What is
h of omega n?
very good. Well, very good, Lawrence. It should be h of omega n. Then it's correct. Okay? So, it's very simple. Right? Do you need me to elaborate this further? How I can get from here to here? I do it term by term. Just imagine if I have one term, I know how to get from here to here. I have two terms, I know how to get from here to here. Three terms gets a little bit more complicated, right? If n terms, takes a long time to finish. Right? So, but if I write as a summation, it becomes very trivial. Okay? So, there is an example in this section, example 5.52. Oh, sorry. Example 5.12. I have an input, f of t, which is equal to n is equal to 1 to infinity. Wow, that is a big number. N is equal to 1 to infinity. If I ask you to compute term by term, it will take you forever to do. Fortunately, you don't have to. You're a smart guy. So you know that the input is something like that. Cosine of 0.5 nt. Okay? What is the output? How should I compute the output? First, I write this in phasor form. If I were to write this in phasor form, I write it term by term. Okay, I find a general form for every term. Then the general form for every term is just equal to that. E to the j t. And what should I insert over here? 0.5 n, very good, 0.5 n. Don't forget the little n there. It could be very, very wrong if you forgot the little n over there. Okay? And now, if the transfer function is equal to that, maybe you can just tell me what the output should be. Okay? How should I change this thing in order to get the output correctly? I would multiply this thing by h of omega, but omega has to be evaluated at the correct frequency, 0.5 n, and then times e to the j 0.5 nt. Okay? That is the output. Okay? Are there any questions regarding this? You just apply the principle of linear superposition. You don't have to do it from 1 to infinity. Just do it for a general term, and then sum up the terms after that. Right? Is this clear? Okay.
Are you going to solve it now?
What is that?
Are you going to solve it now?
No, I don't know how to sum these numbers because it's very difficult to sum infinite series. There are only a few infinite series that can be summed in closed form.
Wouldn't this tend to zero though? No. If you take a limit to infinity, would it tend to zero?
The sum is not zero. The term at infinity is zero. You always have to worry about convergence. Some series are not convergent. Okay, some series are not convergent, whereas some are. Okay, some series are not convergent, whereas some are. And hopefully this series converges. Okay, because it goes to infinity. When n goes to infinity, let's assume that this one goes to 0, or if it's a high-pass filter, it might go to 1 at infinity.
But the 1 over 1 plus n, wouldn't that tend to 0?
Yeah, this will tend to 0.
Wouldn't that make the whole thing tend to 0? It's multiplied
No,
by
this is a sum.
Oh, it's a sum.
It's a sum.
Never mind then.
So if you look at the summand, what you have, it will tend to 1 over n squared. And let's assume that this tends to 1, okay, when n tends to infinity. So if you sum something like this, it converges. Okay, if you sum something like 1 over n squared, n is equal to 1 to infinity, it is finite. Okay, it's finite. It's approximately equal to integration of 0 to infinity of 1 over x squared dx. Okay, maybe some small number. And this can be integrated. It will go as what? 1 over x, right? Or something. And then delta to infinity, and it converges. Okay, you can think of this summation as summing values like this. Okay, and there's 1 over n squared drop off, and summing something like this is like doing an integration. Okay, we do the integration, it converges.
It's pi squared over 6.
You got it?
Yeah.
Who is this genius who summed it? Oh, you got it?
Yeah.
How did you do that?
I put it in my calculator.
Oh. Okay, you have a very smart calculator.
Pi squared over 6.
Okay, pi squared over 6. That I do not know, okay. You can go and check him out when you go home and check him out. Okay? So that's why we disallow calculators in exams. They're too smart.
That is the reason.
So let's do section 5.5 in the last few minutes that we have. Okay, section 5.5, you're given in RLC circuit. And then you have the impedance that looks something like this. R, L, C, and then C input, Z looking this way, will be equal to R plus J omega L plus 1 over J omega C. Okay? And that if you have a transfer function that is make of this, the other one would be actually having the transfer function. If I have this connection state, does this sound right? So if I have connected this one this way, okay, if I have B input, and then if I B out here, let me see, that doesn't sound right. Okay, if I put a current source here, okay, I input, and then if I have a circuit of this manner, then the transfer function will look something like 1 over R plus J omega L plus J omega C. Okay, the transfer function will look something like that. And if you look at this transfer function and work out the details, you find that h of omega can be written as j omega c after you correct for the denominator is 1 omega squared LC plus j omega R L or RC, okay, RC. If you multiply throughout by j omega c, you get that expression over there. And if R equals 0, then the transfer function is equal to this one over here, which is what we have come across before, that of a high-pass filter, okay? So what happens then is that not the high-pass filter actually has a resonance. What happens is that if omega equals to square root of 1 over LC and omega naught, what happens to this transfer function? What happens to this frequency response if omega equals that value?
Denominator is 0.
And denominator is equal to 0, what happens to the transfer function? It's infinite. It's infinitely large. Okay, it's infinitely large. And why does that become infinitely large? Well, if you have this very simple circuit over here, actually, this is not the correct circuit for it. Okay, I have to yet to find a circuit that has this transfer function given by the textbook. Okay, if you have infinitely large transfer function, it means that with 0 input you get an infinite output or some very big output. That is the cause of resonance. Okay, that's the cause of resonance. And it says that resonance transfer functions do not make sense. Okay?